Niels Bohr contributed a great deal to our knowledge of the atomic structure in his model, the Bohr model of the hydrogen atom. He suggested that quantized energy levels existed for electrons, meaning the electrons could only have specific energy values, and that their energy was not continuous within the atom. And he also suggested, or he also helped us understand the relationship between the line spectrum of an atom and the energy levels of the electrons in that atom. However, when Bohr's model was applied to heavier atoms, so atoms with more than one electron, it did not work very well. So in 1924, French physicist Louis de Broglie had a surprising hypothesis. He thought that all objects had wave properties. And the idea was that even a baseball, something as large as a baseball, would have a wave property. However, the mass of the baseball made the wave properties negligible. But then for very small things, tiny things like the electrons, these wave properties could be significant. So other scientists confirmed this hypothesis, showing that electrons do have wave properties. And in 1926, Erwin Schrödinger, who was an Austrian physicist, he created a mathematical model that described the electrons as waves. Using these wave mechanics, we can determine the probability of finding electrons in a certain region around the nucleus of the atom. So this is different than Bohr's model. Now we're looking at finding electrons in terms of the probability that we would find them. So this new branch of physics, we call it wave mechanics or quantum mechanics, and this is the basis of our modern understanding of the atom structure, especially within relationship to the electrons. So when we talk about a probability now, a lot of times they'll talk about an electron cloud, and it will be illustrated as a cloud-like thing because we can't pinpoint the location and the momentum of the electron at the same time. So instead, we're trying to predict a probability. These electron clouds, where the electrons will be, are also called orbital. So the orbitals are the regions of highest probability of finding the electron. Now, the quantum mechanical model is based on mathematics, and at this level, introductory, we're not going to have to dig into the mathematics to show us how it works. So what we're going to do, how I view it, is we're going to pick the fruit of the quantum mechanical model. We're going to take the information we need, the basic information, the results that we can use to help us understand how the electron structure is, so that can help us understand bonding. So in the big picture, our goal is to use this to help us understand bonding. So let's get to the fruit, or the parts that we can use of the quantum mechanical model. So in the quantum mechanical model, when it's solved, you come up with 4 quantum numbers, and those 4 quantum numbers will describe the location of one electron. You heard me correctly. It takes 4 different numbers to describe the electron. So let's kind of go through it and see how they all fit together. I'll tell you, the super cool thing is, once we kind of see how all of these quantum numbers are related to each other, then we can relate those quantum numbers to the periodic table, and it becomes quite easy to see the electron structure of the atom, and then that quite easily helps us understand bonding. So those are kind of goals we're working toward. So there's 4 quantum numbers, and the first one is written here. This is the principal energy level, and it's going to have a letter. It's N, and N, it's a positive number, and the lowest energy is going to be 1, and then it just goes up by 1, 2, 3, 4 whole numbers, and it just keeps on going. And you can see in the picture, the lowest level down here is 1. That would be closest to the nucleus, and the higher the number gets, the farther away you get from the nucleus. And in this example, and most of the things we do in class, 4 will be the highest that we would end up going to. So this is the principal energy level. Now, if you want to kind of put these numbers together, remember we're trying to describe where the electron is. So if you imagine a building, and our building is going to hold the electrons, these energy levels would be like telling you what floor you're on. So if I said, oh, you're in n equals 2, then that kind of tells you, okay, you're on the second floor. So we're 2 floors above where the nucleus is. So the energy level kind of tells us, an analogy might be the floor of a building. So the second quantum number is called the orbital angular momentum quantum number. It's designated by an L. And what we're going to call these, I mentioned this name because if you take Chem 1, that's what it's called. But these to us, when we look, if you look in your textbook and when they're talking about it, these are called the sublevels. And the sublevels can range or have 4 different designations. They can have the letters S, P, D, and F. These letters actually stand for something. The S stands for sharp, the P stands for principal, the D for diffuse, and the F for fundamental. That's not important to us, but just to give you an idea of that those are not random letters. They stand for a word. Now what you can notice, in the solution, what they find is that the number of sublevels is equal to the energy level you're on. So let me phrase that a different way. So see down here, this is the first energy level. This is energy level 1, and you'll notice there's only one sublevel, and that first sublevel is an S. Okay, the lowest energy in any level always is S, and then as you go to P, D, and F, you increase your energy. Now then the second energy level, if you think about it right here, that's the second level. It contains 2 sublevels. It also has an S and has the P. Now the numbers in front of the S's and the P's are not telling you how many, it's identifying what level you're in. So when I see 2S, I identify that it's in the energy level of 2. It would be like if I told you in our classroom is in room 218, and you would recognize that it's on the second floor because it starts with the 2. You know, if the room number was 418 and we don't have 4 stories, it's kind of a little bit confusing. But this is not confusing. You can see here on the third level there are 3 sublevels. And they all have the 3 in front of it. That tells you you're in the third energy level. And then the fourth energy level has the 4. So what you'll notice about all of them, they all contain an S sublevel. And then as you build, then you add the P's next, then the D's and the F's. So I imagine, again, if you're imagining a building with me, to try to remember, we're trying to get where the electrons are. The energy level tells you the floor of the building you're on. These sublevels would be like a room. So if you imagine a building, you walk in and there's different rooms, and there might be the S room and the P room, depending on what floor you're on. So these sublevels tell us a room. So we're getting a little bit closer to where the electrons are. The third quantum number is the magnetic quantum number, and we will designate these as our orbitals. So orbitals are kind of like the chairs. We're finally getting to where the electrons would actually sit, and in the orbital you can have 2 electrons in each orbital. Okay, 2 electrons in each orbital. So that's the maximum number of electrons that we can have in one orbital. And so that's called Hund's rule. Sorry, that's not Hund's rule. I apologize. That's the Pauli exclusion principle. So scrap that. The 2 electrons in each orbital. I'll write it here. It's a Pauli exclusion principle. Okay, so let's get back to orbitals. So we have the orbitals also have letter designations the same as the sublevels. So you can have s orbitals, and s orbitals would be inside s sublevels. You can have p orbitals, and if you look down here, there are 3 p orbitals, and then we can have d orbitals here, and there's 5 of them here, and then we do have f's, which they don't have pictures. So here's something that is we need to know, that if you're in an s sublevel, you have an s orbital, and there's only gonna ever be one. An s orbital has a shape of a sphere, and even when we rotate it in 3-dimensional space, it always looks the same. Now p orbitals, they come in groups of 3. So they look like these dumbbell shapes. The flower up here would kind of show you what they would look like all together. The d orbitals come in groups of 5. And then f, which we don't have a picture of, come in groups of 7. So let's think about this then. If I can put 2 electrons in each orbital, if I'm in an s, I can fit a maximum of 2 electrons. Right? If I'm in a p, because there's a p sublevel, because there's 3 orbitals inside, if you think there's 2 in this one, 2 in this one, and 2 in this one, then we can have a maximum of 6 electrons inside of the p. Now the d, in the d sublevel, we can have 5 d orbitals. D, each orbital can have 2 electrons, so that's 2, 4, 6, 8, 10. We can have 10 electrons when we're in the d sublevel, and f has 7 orbitals, so that could have up to 14 electrons. Now this is where the electrons are going to reside, are inside the orbitals. So if I imagine my building, finally we'd get to the chairs in the rooms, and that's where the electrons would sit. Okay, so we have the principal energy level, which tells us that that's the end. That tells us the 1, 2, 3, 4. We have the sublevels. That tells us what room we're in, right? And those are labeled S, P, D, and F. And then we have the orbitals that are inside the sublevels, and that's where the electrons are. And if we're in an S, we only have 1 orbital. We can hold 2 electrons. P always has 3. D has 5, and F has 7. So let's see if we can put this together. So if I have the energy level, this I could have 1, 2, 3, 4, and then 1 only has 1 sublevel. It's the 1s. S only has 2 electrons, so in the first energy level, the maximum number of electrons I can have is 2. That's the first level. Now the second level can have 2 sublevels. So I have an S or I have a P. Now remember, the P orbitals, there are 3 of them. This whole thing right here in the box, that's the sublevel, but there's 3 p orbitals inside of it. So I could have 2 electrons in the s and 6 electrons in the p's. So in the second level, I can have 8 electrons maximum. Okay, so when we talk about sublevels, well, let me do it on the 3. I'll do it again. So 3 has 3s, it has 3p, which has 3 orbitals, and it also has, you have 3 sublevels, so I have 3 ds, and ds have 5 orbitals. So I'm going to change the color here. So like if I just look at an individual one, that guy right there in red, that is an orbital. And any orbital can contain 2 electrons. This D over here, any of the D's I could pick, this is an orbital. And even though it's a 3D, it also contains 2 electrons. And even this S right here, that is an orbital. And that contains 2 electrons. Okay, well we also then have sublevels. So a sublevel is any orbitals that have the same number and letter. So the P's, I'm going to put it in a box. All of them together, that's the sublevel. And if you're a P, that has 6 electrons. The D's, the sublevel, is all of these orbitals together. That's a 3D sublevel. So that sublevel has 14 electrons. And the S is kind of a funny guy because it only has 1 orbital. So the orbital and the sublevel both have just 2 because there's only 1 in there. So if I'm looking at this third level, let's see, I kind of have to write over here. The S can have 2. The P's can have 6 electrons. The D's can have 14 electrons. I'm sorry, 10. My pen is distracting me. 10 electrons. So total, that is a total of 18 electrons on the third level. I'm moving my 4 up a little bit higher. Now hopefully you're seeing the pattern. 4, I have to write them small because I'm crowded. 4 has the 4s. Then it also has P. It's going to have 4 sublevels because it's 4. Then it would have the D's, and it would have 5 of those D orbitals in that sublevel. 1, 2, 3, 4, 5. And then the F's, 1, 2, there'd be 7. 3, I'm sorry, I'm too top at the close. I'm at the top and it's causing me trouble. 4, 5, 6, 7. I snuck it in there. So we would have 2 electrons in the 4 S's, 6 electrons total in the P's, 10 electrons in the D's, and 18 electrons. So the fourth level could hold up to 32 electrons, which makes sense. The further you get away from the nucleus, the bigger the volume of space is, and so it makes sense that you could hold more electrons. So how this all fits together and how it fits with what we call electron configurations and how it fits together with the periodic table is going to be in the next video. So in this video, what you want to do is kind of get down the words orbitals, sublevels, levels, how many electrons can go into each, and try to kind of start to see the organization. In the next video, we'll take a look at how that organization then can be applied to what we call electron configurations and the periodic table.